Imagine, for a moment, standing at the very edge of everything we know. Not just the edge of our galaxy or even our local cluster, but truly gazing out into the vast cosmic tapestry of the universe. What you see is not static, not a frozen tableau of stars and nebulae. Instead, this immense cosmic ocean is stretching, expanding in every direction. And what's even more astonishing, it's doing so at an ever-increasing pace. It's as if an invisible, unknown force is steadily pushing the very fabric of space and time apart, accelerating the separation of galaxies, ensuring that the farther we look, the faster everything recedes from our view. For decades, this accelerating expansion has been one of cosmology's deepest and most perplexing enigmas. We've given this mysterious cosmic accelerator a name: dark energy. It's a placeholder, really, a label for the unknown, for the dominant force that comprises an astonishing 2/3 of the universe's total energy density. Yet, despite its profound influence on the cosmos, we have no direct evidence of what dark energy actually is, where it comes from, or precisely how it orchestrates this grand, accelerating cosmic ballet. It remains one of the greatest unsolved mysteries in science, a fundamental gap in our understanding of the universe we inhabit. But what if, just perhaps, our understanding of the universe is about to undergo a subtle yet profound shift? What if the answer to dark energy isn't some exotic, undiscovered particle or field, but rather something far more familiar, something already woven into the very fabric of our physical laws? This is the tantalizing prospect offered by a trailblazing new theory, conceived by Swiss physicist Claudia de Rham. Her work invites us to reconsider one of the most fundamental forces of nature: gravity itself. De Rham has put forward an idea she calls massive gravity. It's a theory built upon the bedrock of Einstein's general relativity, which elegantly describes gravity as the curvature of spacetime. But de Rham and her colleagues introduce a crucial, subtle modification. To truly appreciate its significance, we first need to touch upon the microscopic world of particles that some physicists believe mediate forces. When we think of light, we think of photons, tiny packets of energy. For gravity, particle physicists have long theorized the existence of gravitons. These are hypothetical particles believed to be the carriers of the gravitational force. For decades, the prevailing assumption has been that, much like photons, gravitons are massless. It's a detail that, at first glance, might seem like a mere technicality, something only relevant to the most esoteric corners of theoretical physics. But here's where de Rham's theory takes a radical turn. She and her team propose that gravitons, unlike their massless cousins, actually do possess a tiny, almost imperceptible mass. This might indeed sound like physicists splitting hairs, a debate over an infinitely small quantity. However, the implications of massive gravitons could be nothing short of revolutionary, especially when it comes to the enigma of dark energy. As dark energy herself has explained, one possibility is that you may not need to have dark energy, or rather, gravity itself fulfills that role. Consider the profound elegance of this idea. Instead of inventing a completely new, unknown entity to explain the universe's accelerating expansion, de Rham's theory suggests that the very force we thought we understood, gravity, could be responsible. If gravitons have mass, it subtly changes how gravity behaves over immense cosmic distances. Think of it this way. If gravity's messenger particles have even a minuscule mass, their influence might diminish or change its character more significantly across the vast voids of intergalactic space than previously thought. This slight alteration could, in effect, generate a repulsion or an accelerating expansion that perfectly mimics the effects we currently attribute to dark energy. It transforms a cosmic mystery into a nuanced characteristic of one of nature's most fundamental forces. Right now, massive gravity remains a theoretical construct, an elegant mathematical framework. But the beauty of scientific inquiry lies in its relentless pursuit of empirical evidence. As our technological capabilities advance, particularly in the realm of detecting gravitational waves, the ripples in spacetime predicted by Einstein and now observed, scientists may soon have the tools to put de Rhams' cosmic speculation to the test. Imagine the thrill, the intellectual satisfaction, if we could detect subtle signatures in gravitational wave observations that confirm the mass of gravitons, thus potentially unveiling the true nature of dark energy. This journey into massive gravity reminds us that our understanding of the cosmos is perpetually evolving. What we consider settled truth today might be a springboard for tomorrow's groundbreaking discoveries. It's a testament to the human spirit of inquiry, constantly questioning, refining, and daring to look at the familiar in a completely new light. The universe is a grand puzzle, and each new theory, each new observation brings us a little closer to deciphering its most profound secrets. So, the next time you gaze up at the night sky, consider the possibility that the very force pulling galaxies together might, under different cosmic circumstances, also be the force pushing them apart. What are your thoughts on this intriguing possibility? Do you find the idea of gravity itself being the answer to dark energy compelling? Or do you think the universe holds even more exotic surprises? Share your reflections in the comments below, and let's continue to explore these profound questions together.